Okay, hello everyone. Welcome to the EPANET tutorial for the MSc Water Supply and Distribution Systems course at Imperial College London. My name is Bradley Jenks, and so today we'll be going through a hands-on example with one of the networks that's been provided you in class, or on Blackboard rather, and you'll also have access to this slide deck. So we won't go through all the material that's in this this presentation. So the first bit will review basic hydraulic modeling concepts and terminology. All of this will be presented during lecture from Dr. Ivan Stoyanov, but this is just to give you additional reference resources to be able to facilitate your learning of EPANET. So as I said, we'll focus on the software itself. Now I'd first like to show you where, so today's tutorial will walk through a specific example, but it won't be comprehensive. So if you need additional information, you can go and search for the EPANET 2.2, so its current version's manual. So if you go there, you'll be able to find this document, which is quite extensive, so you'll be able to go through and look at specific problems that you may have, either here or in the future. Okay, so we'll jump ahead to the tasks that we've asked you to do for your homework network. So the first one we'll be looking at running the hydraulic simulation. So we'll go through on how we will do that in the software, and we'll visualize pressure at different times, flow and pressure rather, at different times throughout the day, and understanding how this changes and how the software can help us demonstrate this. And so we'll briefly describe those differences. The second task we'll look at connectivity, or what's commonly known as a critical link analysis. So what happens if we close a certain link in the network, or in reality there's a blockage or the pipe bursts, and so this no longer can convey flow to its downstream node. So we'll look at the impacts on pressure by closing the source links, as well as a critical link that we've chosen for you later on in this slide deck. And then we'll look at head loss throughout the network. And so both looking at the distributed or frictional losses. If we modify the roughness coefficients, what impact does that have on the network? And then we'll also look at introducing a local loss, so a blockage or a partially opened or partially closed rather valve, and what impact that has downstream. And then we'll look at also simulating a burst. And this is done through an emitter type junction, where we can set a large coefficient, which will then simulate a burst in the network, so a very large demand, and what the impacts that has on the network's hydraulics. So there's some additional information here that you can use as a reference, and again, throughout the many material, lots of material online or in the EPANET manual. We'll walk through these concepts exactly, but they're here for your resource as well, reference there. And we'll come back to how local losses are modeled in EPANET in a moment, but let's get into the assignment. So in-class assignment. So here's our network, and here are some information that will be used to close certain links and introduce head losses at others, and introduce a burst at a certain junction. So we'll go ahead and open up this network. So this is the Pescara. You'll want to open the .imp file. So here's our network. We'll quickly walk through the interface of EPANET first. So starting with the top, here we can view, so we have zoom. We can view its full extent, so we can zoom in on a particular. So coming down from view, here's our main toolbar heading. So we can zoom in on a particular area. We can then use the pan tool to pan where we need to go. We can equally zoom out. So we can just click to zoom out one level, or we can specify the extents that we want to zoom. And then the farthest right on this panel is full extent, so this will take you back to that initial viewing. Project, so we click summary. This will tell us, so the titles of who created this network. So this is a very well published network in the literature. You can view this reference for further information if you so choose. And then there's statistics on the components of the network, so the number of junctions, reservoirs, etc. It also gives you the units that are used, so liters per second. So we're using metric in this particular example, but this may be Imperial for those using the software in the US. The head loss formula that's used, so we talked about this briefly in class, Hayes and Williams or the Darcy-Weisbach, and quality parameters. So in this case, we're not running a water quality simulation, but there are various different ways you can go about doing this, and we won't discuss that in this tutorial. We're just looking at hydraulics. On the furthest right of this panel, we can create elements. So here we're giving you the network. It's been created for you, and this is an operational network or representing an operational network. So you're not building the network from scratch, but if you were to do so, you have these tools up here. So you to create your junctions and your source and so forth, in connecting that the network, as you see here, with various links, so pipes, pumps, or valves. So for our purposes, we will delete these. So looking at the specific properties of the network components, we'll start with a junction. So we'll click here, junction 58. There are two ways to view the properties, well, three ways. We'll go to here first in the EPANET interface, and then we'll look at the .imp file in a text editor to review how we can change properties there as well. But for the first instance, we can double click on the element, and that will pop up its properties. And so the first thing to note here is the cells in white. These are the ones that are our inputs to the model, and in yellow, these are the outputs of the simulation. And so right now we haven't run a simulation, and that's why you'll see not applicable values. So we have our junction ID at the top. We have its location, its x and y coordinate. We have its elevation, which of course is important for computing our hydraulic grade line. Its base demand. So as we've talked about in class, so the base demand is associated with a demand pattern. So if we look at this pattern, demand pattern 1, we'll come back to this, but what this is doing is our base demand is multiplied by a demand profile throughout the extended period simulation that we're running. So here we have 24 discrete hydraulic time steps, and for each time step we have a pattern or a multiplier that will multiply by this base demand to give the actual demand at time step 1. So we'll review where the patterns are stored in a moment, but that's for all demand nodes. So each demand node you can imagine, we have a spatial distribution. So we're looking at junction 58, which has a particular base demand. If we look at junction 22, it will have a different base demand, and they'll both change temporally with a certain pattern, or a pattern that's assigned to it. So in our case, our temporal, or our period, is a 24 discrete 1-hour intervals that we're looking at. So these are 24 steady state snapshots in time. And they may have different patterns, and so to add different demands with different patterns at one particular node, we can add different demand categories. And so here is a drop down. So we only have one at this particular node. It has a base demand of this value, and we have a pattern associated based on the hydraulic simulation time. But we can see here that we can add multiple demands, and whether we have the same pattern or different patterns is up to the user. We'll just keep this for our purposes. Then we have an emitter coefficient, so we'll look at this more specifically when we model a burst. We'll come back. And then we have quality parameters. Excuse me. That we'll ignore for now, but you can look at the manual for further information in the future how water quality is modeled in the network. So as we double clicked on the junction, we can also come up here to the browser window. So this is also where all the information of the network is stored. So if you look at the first tab, which is data, then we have our drop down of the various components. So we looked at junction and we looked at junction 58. So we will jump to which one's being selected. Equally, we can look at, we said 22. So we can come to junction 22 and you can see the highlighted cursor jump around as we did that process. So we can double click on this and look at the same properties. So just for comparison, you can see here that our base demand is much higher at this particular location, but we're using the same pattern. So on the note of pattern, if we come back to our data and we come down to patterns, we only have one pattern in this network. And if we double click it, we can see the multipliers throughout that 24-hour period that we discussed. So, excuse me, when the simulation is at time step 1, all of the demands that have this particular pattern, so pattern 1 associated with it, will be multiplied by this value in this cell, and so forth throughout the day. Next thing I want to look at is the reservoir information. So this is the source to the network. Again, if we double click, it'll go right, as you can see here, to data, reservoirs, and the particular one that we've selected. We double click. We get information on its location again, and we get the total head value. So this is the, for our purposes, elevation and just elevation, right? Because the reservoir is open to the atmosphere, and so our hydraulic head, which here is total head. Again, this, make sure to familiarize yourself between energy and energy grade line and hydraulic grade line. Of course, at a reservoir, there's no velocity, so they're equivalent. And this is representing that total head into the network. So we have a value here. In some cases, we'll also have a pattern associated with this value. So if there's no pattern, that means that over the 24-hour period, so each 1 hour time step, this value is constant. If we have a head pattern, then it will vary throughout the day. So you'll have a multiplier for each time step, just like your demands, and that value will change. And then lastly, we'll quickly look at pipe information. So let's go to pipe 1. Convenient. Same information, labels, the start and end node. So this is a convention that we have assigned. It may not be correct. So if we simulate the way to know if it's not, so we've assumed that the flow path goes from node 1 to node 2. This may not be correct depending on the hydraulics of the network after we simulate it. And so if we get a negative value for flow, this just means that we've assumed incorrect our convention and the flow path is in the reverse direction. That's all it means. So it's fine to assume something. Just note that negative values just mean that it's opposite to the convention that you've assigned. We have pipe properties. So these are important for computing the frictional losses across that are materialized from flow being conveyed across the pipe link. So we have its length, its diameter. So its length, because we're in units of liters per second, our length is in meters, our diameter is in millimeters, and our roughness, so in this case we're using the Hazen-Williams model as we looked at the project summary. And so this has some units that you can look at on your own time. But if we were using the Darcy-Weisbach model, this would be the pipe roughness, so this would have the millimeters units. And then loss coefficient across the valve. And so if we want to model a localized loss as presented in the slide deck, we can add a coefficient to include that loss. Initial status, so as we'll test in a moment, we can either say we have open, so it's open for flow to be conveyed across it, or closed. So this just means that it doesn't exist in the network, and flow will have to be rerouted a different path. A CV, we won't simulate this, but this stands for check valve. So this implies that if the flow direction, the convention we've assigned, so here we say it goes from node 1 to node 2, that has to be the case where we won't allow flow in the opposite direction. So if the hydraulics dictate that flow is not conveyed in the direction that we have assigned, then it will act as a closed link. And vice versa, it will permit flow if it's in the right convention. But we won't look at that any further. And then bulk and wall coefficient are water quality parameters, so we won't discuss those. And then you can see the values that we get as a result of the simulation. Okay, so to simulate the hydraulic model, and in the lectures, you'll go into much more detail how the system of equations, so mass and energy, conservation of mass at network nodes, and conservation of energy across links. You'll go into the details of how those are formulated and the numerical method that's employed to solve it. But for here, we'll treat it as a bit of a black box and run the simulation. So this is up with the lightning bolt symbol up here. So we click that, we see run was successful, and now we can look at the results of the simulation. So first we'll look at, now we can see that the yellow cells are populated. So we have our actual demand. Our actual demand, of course, isn't equal to our base demand. That's because we have our time pattern at that specific, so at midnight or time step 1. We have the multiplier to this, so it's obviously going to be lower during the overnight period. We have our total head and our pressure head, which is just the difference based on the elevation here. So to view the simulation, our first task, if we go back here in class assignment, we go back a few. So we want to visualize pressure and flow at 3 a.m. and 8 a.m. and describe the differences in hydraulic conditions. So if we come up back to our browser tab, when we click on map, we have different values that we can present in the network. So let's go get our nodes and we'll go to pressure. And you can see that color, so you have a legend defining the color bands for different pressure values. So let's first, sorry, I want to do one quick thing here to make it a bit more visible. If we go to view, options, we can increase the size of our nodes, and we'll do the same thing for links. Let's do this. There we go, a bit more readable. So our legend, if we right click, we can change the intervals that we want. So we can do this manually. We can set equal intervals. Let's just do that for the sake of our visualization. We can reverse the colors. So, intuitively, red most often means bad, and so low pressure, we'll assign that bad connotation. So we'll reverse the color, and there we can visualize our pressures in the network. So the first thing to notice is that if our the source, the largest amount of energy is coming from the reservoirs, why are they red? Well, this is the case because we are open to atmosphere, so the pressure is 0. If we were to instead go to head, now that's much different. So now we can, now we have inappropriate energy grade line. So we start here at a higher head, we come down, flow path, lower, and so forth. Different reservoirs, of course, have different starting. So this has 57 meters. Now this is 53. So this is providing more supply to this part of the network. Okay, so let's go back to pressure. We've got our, and we want to look at 3 a.m. So you can see here that our, what we'll get you to do okay, so what we'll get you to do is also we want to look at the flow rates. So we'll have flow here. We'll set this equal interval, so this will just take the maximum and distribute accordingly. So we'll do one at a time because it gets a bit too much. So we'll say no view. Time 3 o'clock. Okay, so what you'll do on your in your assignment is you'll look at these values and how they're distributed between these two different time steps. So we can see here that we have the highest pressure in the northeast area of the network, and this becomes lower as we go to the different areas. So if we were to now change to 8 o'clock, we can see here that the pressure has, whoa. No, this makes sense. So the pressure is decreased. So lighter blue, slightly confused. Dark blue means largest pressure, and so our the pressure is decreased between these different time steps, and this makes sense because we have more flow at the higher demand period 8 a.m. So actually, one way to quickly check this before we look at flow, so you'll be able to comment on these differences, look at different areas of the network. So you can see here, up here, we had the lighter blue sky or cyan, I believe, and now we're at green, so we're at a lower pressure, as expected. So we can actually go up to the top. You'll see a graph symbol. So we click that, and we want to look at system flow. So to be able to look at the total flow, inflow to the network across the simulation period, we can view that here. So this is our system flow balance. And we can look at, we were viewing 3 a.m., so this is the minimum period. As you've looked at in class, this minimum night flow, which is an indicator of leakage, and this is when we're consuming the least amount. And then up and through 8 a.m., here is when we're consuming the most. But so we see that in our pressure plots as the head loss has been increased. So now if we get rid of pressure, and we look at flow, so we've set this up. So this is, let's go back. Well, we start with 8 a.m. So blue being the least amount of flow, red being the most. Now this makes sense that the most amount of flow is coming from our reservoirs. This is with a source. So all the demands at one point have come from a reservoir, of course. And we can see the distribution throughout the network. So more flow looks to be coming from here and providing this area, whereas here we can look at the flow path, and this is providing the upper northwest corner. What we can also do to look at the flow paths, so we can go options, just like we increase the size, we can go down here and click flow arrows, and you can look at different styles and size. We'll just do the basic one for now, and we can see the actual paths that flow is taking. And that's interesting where we see this kind of hydraulic balance point where flow from this reservoir is being met somewhere around here, and we can look at the influence of the reservoir to the east as well. And so that's something you can comment on in your homework assignment. Okay, wanted to go to 3 a.m. You can see how that changes. So now the flow from the sources has been decreased quite a bit. Okay, so now the second task we've asked you to do is looked at a connectivity or critical link analysis. So we'll test the impacts of closing each of the source links. And if we go to the end of the slide deck, we'll see the source links that we want you to close. They should be intuitive based on where the reservoirs are placed. And then as well, we'll look at a critical link. So if we come back, and go no view, and we want to go back here. Let's get rid of the options. Get rid of these arrows for now. Okay, so now if we were to close, so you saw pipe 54 was one of them. If we were to double click it, and we were to go to its initial status, and we hit closed. And let's actually go back to pressure. Actually, the first one is obviously flow. We'll see that. We'll make sure that no flow comes from here. So you'll see at this is negative pressures. Yes, this makes sense. Okay, so We've simulated the network now with this pipe 54 closed, so we have zero flow. That's confirmed, and our status is closed. So we've inputted closed, and it's seen that as a possible option. Got an error with the simulation, which said negative pressures at the first time step. So if we go to look at our, let's get rid of our flow. We've established that there's no flow across this link. That's good. We can go to pressure and look at that. So now we have, if we change this, so let's say we want, we said our minimum was 15 meters in our assignment, so let's keep it at 15 meters. Well, actually, even better, let's do go and do 0. So all of these okay, sorry about that. So all of these pressures, these nodes have negative pressure. So the supply across from our reservoir to the east is not, it does not have enough energy to supply this part of the network across this flow path. So what would happen in reality, of course, we wouldn't have negative pressures. We would have, our demands would not be able to be met. So we won't go into detail about the difference. Here is what we call a demand-driven analysis or demand-driven simulation. So this is when we set our demands. So as we've seen here, we have a base demand, and we expect to receive that outflow at that particular junction. But if we don't have enough pressure to supply that demand, then of course we won't be able to pull water out at that particular point in the network. So that's when we transfer to a pressure-driven simulation or pressure-driven analysis, when we can only take enough water out that the system is willing to give us. And that's on the available pressure at that node. And so that follows an orifice type flow, where the square of the pressure head at that point is what we can more or less take out of the system. But in this analysis, it's demand driven. So we're telling the software, we're telling the model that we must meet this demand. So in order to meet that demand, we have quite a large negative pressure, which of course isn't true. So this is one of the times that if we had a break, this is a critical link, we would not be, we would transfer to a pressure-driven simulation to be able to see at the given pressures from the other, that are able to be provided from the other sources, what demand could be really taken from the system. So we won't go into details on that. You can go into the EPANET manual to look more on that, or have discussions with us in class. So the result here is that we cannot, this is a critical reservoir to supply this part of the network. So if we go back to open it, run the simulation again just to make sure that we're okay. Yes, we are. If we go to now our reservoir here, and we do the same thing, close, go back to the extent, and we simulate, warning, reservoir is closed, and we can see the impacts. Okay, so when we close the second reservoir, reservoir 15, or the pipe connecting it to the network, we see here at the first time step, we're actually able to provide, so the other sources are able to provide flow and have enough energy to provide flow throughout the network. So we don't get any negative pressures, as we can see here. And so where is the flow coming from? Well, you can turn on the flow direction arrows to facilitate that analysis. You can see from the south reservoir, we have providing flow, and then across this these links here that connect kind of the west and the east parts of the network. So if we change though, when you simulate it, you'll see the report or the error specifically in the simulation, and it told us that at 8 we got negative pressures. Yes, and so you can imagine this is the case as the demands are increased. So at 8 o'clock we have higher demands, of course, and that's causing the pressure to be. So we're pulling more of the system. We have more head loss as a result. and that's causing our negative pressures. Okay, so you can continue this exercise on. I won't go through the last reservoir. What I will show quickly is if we get rid of this, we open this back, and I believe we had a critical link 38. So in addition to the links connecting the sources to the network, we also have different critical links that we can look at, and this is the basis of a what-if analysis. So if this link breaks, we have various metrics to select these critical links based on the simulation results. But here we're gonna select that for you. So I think it said link 38. Link 38. There we go. Double click this. We can set its initial status to closed. We can come back to extents and run the simulation. Run was successful. Okay. So you can see that there is now no flow between the two. Obviously across this link, so we have double check, zero flow, and you can see the impacts it has to the network. So at some parts of the day, so during low demand, it seems to be okay. If we go to peak demand or higher demand, we can see the pressure distribution during that period, and so with no flow across here. So your job is to compare these results to when we have it open, so in your initial simulations, and look at the impacts. So the result of this is if this pipe is cut off from the network, there's a burst, and we cannot convey water across it, is it going to have a adverse impact to the rest of the system? Okay. So we will go back and view. Okay, so that's looking at the critical link analysis. The next task that we wanted to do is look at head loss. So we'll first, before we get into introducing local head loss, I'd like to, and as I mentioned this earlier that I didn't go back to, the task, we won't simulate the results, but we'll go through how to more effective ways to input these changes. When we look at a sensitivity analysis, so if we want to change the pipe roughness coefficients by 50% to increase head loss, well, in our case, we're looking at we're using the Hazen-Williams model, so we have our Hazen-Williams coefficient that we're changing. So if we want to increase head loss, we go to our Hazen-Williams equation. It's inversely proportional to our head loss, so we want to decrease. We want to decrease our coefficient, and the opposite will be true for the Darcy-Weisbach. And the Darcy-Weisbach will be used in your take-home assignment, so keep that in mind when you work through that. So 50%. Now it would be quite tedious to go to each link, go to the roughness, and multiply by 50% or reduce, or in this case, in our case, reduce the roughness coefficient. So instead, what we can do, if we select this, open up Excel, open up a spreadsheet, and we can open the .imp file as a text file or as a CSV. So if we go to open, let's go to 1 second, sorry. EPANET tutorial networks. So we can go to all files and we can open it. We'll open the network that was shown in class just because we can't open this file. If we go to open Pescara, which we have open in EPANET, we obviously won't allow us to do that because it's already active. So if we open this, so we can open this as a CSV. We want yes, finish. So all our network data that we have described, so it's either you can use the map interface or in data, is all listed in this format here. So we have our junctions, we have the IDs, elevations, demand, and so forth, reservoir information, pipes, and other information as well. So you can go through in your own time and look and compare with the software, but everything's here. So you can equally change things in the .mp file directly here. So you have your roughness. If we wanted to increase the head loss, we wanted to simply go here, 0.5. So now we increase the head loss. And so forth. Which this, I believe this copy, I've already done this because this is not a practical value for Hazel-Williams coefficient. So I believe what the initial values were 110, etc. So I've already halved the Hazel-Williams coefficient here. But in any case, you get the point to be able to do this in a much more efficient manner. So then you can save it as .mp and open it, and these will be adjusted in the model. So we can come back here. But in our tutorial, we want to introduce a local loss. Click back here. Oops. Introduce a local loss at link 84. Okay, so before we go into EPANET, we should go quickly through how local loss coefficients are inputted into EPANET. So we have two types of links that we can do this. One is at a pipe and one is at a valve. So our local loss coefficient is looking at an open. So if we had a valve, we either, let's go back. So for pipe links, which we're looking at, we directly add this loss coefficient, so this K value, into the loss coefficient input cell. And it was very low initially. So if we look at, first of all, if we look at so we want to do that link 84. So we go into EPANET, pipes, link 84. Bit of a side note, one way, if this network was massive and we didn't know where link 84 was, we can go into binoculars, find link, we can type in 84, find, and it'll show us where that is. So that is up in this area of the network here. Okay, so we want to add a local loss here, and this is a pipe link. So let's get rid of this. So we have our local loss coefficient, which is set to 0. Its initial status is open. So for pipe links, we directly add this loss coefficient to this in this cell, and then that follows the local loss coefficient and how these are generated in the model follows the equation here, and where K is a multiplier of the velocity head, and this depends on valve or if we're trying to simulate a blockage or other local loss phenomena, then we'll input that value here. So we can adjust that and look at the sensitivity it has on the network, or rather the head loss across that link. So you can go, different valves have different properties for this, and you can look at a partially closed valve, so you can relate its K value to the opening or closure percentage. We won't get the details there, but we'll for our purposes, we're just inputting this K value. So we can come here and add, we'll add 100 and see what happens. Again, the specifics are important when you're modeling a specific condition, but for us, we're just looking at the sensitivity or what the changes are in flow across this link. Equally, if we wanted to look at a valve link, if we come back, valve link, its intent, as you've had lectures on this with in the previous sessions, is to control the pressure. And so therefore we have various types of valves. So the TCV here is just a throttle control valve. But when we have our valve is open, if we have our valve as open, then it acts as a pipe. So it's not active. We're not actively controlling pressure. If we have this fixed status, if we set this to active, then the local loss coefficient is not used, but rather the setting of the valve is used. So if we demonstrate this, so in this case we have a pipe, local loss coefficient, we have our value. We're okay with that. Let's delete this for now. We're going to create just for purpose of demonstration, we will connect a valve from here to here. So there's no simulation results, of course, because we just added this element to the network. And in fact, if we have no demand here, then it's won't be able to simulate because we have no flow across the link. But I just want to show you how we would input these properties. So if we're looking at a pressure reducing valve, PRV, there are very different valve types. And you can go through the manual or the lecture slides to be able to understand the purposes for all these different control valves. But we'll keep the PRV for now. So if we have its fixed status, and it says none, none means that it's active. So when you have the status here, it'll show up as active at the bottom. So you're telling the model that we have a PRV with a certain setting, so we want to reduce the pressure to a certain value. Loss coefficient is not active in this case. Your setting will be. If we set this to closed, well, of course, just like a link, there'll be no flow and no pressure control across this link. So that's quite intuitive. If we set this to open, then we have no pressure control capabilities at this link. It's now acts based on its properties, so you have your diameter. It'll assign a unit length, and our head loss will be calculated based on the loss coefficient that you give it. So I hope that makes sense, and you can review in detail in the EPANET manual. But those are the differences between our valve links and our pipe links in terms of its local head loss and how it's modeled. So valves, we're controlling. So when we control, we can set based on different control objectives. Here we're reducing the pressure at the downstream end, and we can control that setting accordingly. If we set this to open, then we're not a control valve anymore. We're just a pipe where we're conveying flow in the network just as a pipe would. And then the loss coefficient comes into play. Okay, so we're going to delete this. Delete. Pipe 84. So we'll add a loss coefficient of 100, and we'll see what happens. So go back to simulate. Run was successful. Map. Just as we've done before, we can look at pressure. We double click the pipe and we can look at the head loss across the pipe, the local loss that's been introduced. And so we can see here the unit head loss, 1.2 meters. So if we were to instead increase this to 1,000, again, these numbers are just acting as a sensitivity analysis for us. And we simulate. Okay. Head loss, 5 meters. And so you can see the impacts of the network. Because there are multiple other flow paths to provide flow here, you won't see much of a difference in pressure heads between these two nodes, but we will see a reduction in flow rate, right? So we have 6.545. If we were to increase this even more, our flow's gone down because there's more resistance across this link. There's a blockage or a valve is partially closed, and our head loss is going up. So this makes sense. So what you'll do is you'll comment on what impacts this has on the overall network hydraulics. So the demand still needs to be met at these downstream nodes. So how is the flow redistributed based on the local losses that are encountered here? Okay, so we'll come back here. And you can plot these properties for different, so I mean, as a sensitivity analysis would do is you can plot for different local loss coefficients, what impacts you get in the network, what flow or head loss is encountered across that link. Okay, so that's that. So our last task looks at simulating a burst. So this is what we'll do to do that. What we'll do to simulate this in EPANET is through an emitter junction. So we have this slide here to be able to go through this pressure dependent flow. So emitters are devices assigned to junctions for modeling pressure-dependent flow. So a burst, we don't know what this burst, or we want to see how much outflow can be simulated from this burst, and that's on the basis of the available pressure in the network. So this isn't a demand that we know as an input to the model. It's a demand that we are looking at trying to simulate, or what could the burst flow be based on the network pressures. So this follows our orifice type flow. So our flow rate is based on our available pressure head at that junction or at that point in the network, and the square of that. So by default we're using 0.5, and C is our discharge coefficient. So you can think of C, if you think back to the orifice equation, as our discharge coefficient, so our CD, times the area. So this is aggregating those two terms together. And the reason being is that we are less concerned with the actual properties of the burst, so how large in diameter the opening is, and its discharge coefficient. We're most concerned with just the sensitivity of this. So if we were to assign a large value, what happens across the network? So we can easily do this by changing the coefficient C. So a large C can be used to model pipe bursts. And just like we did with the local loss coefficient, we can change this value and look at the sensitivity across the network and the pressure conditions that it causes. So junction number one. So if we come to junction number one, again, let's do this properly so we can find node number one, and that's right at the end of the network here. So we have our emitter coefficient. Emitter coefficient we can set to do a bit of a sensitivity analysis. Why don't we start with 10? So if we look at the actual demand of this node is 1.4 liters per second at midnight. And so if we add a emitter coefficient here, so we have some pressure dependent flow, we can see how that changes the network hydraulics. So we have pressure of 46.5 meters. Let's look at how that changes. Successful, so you can see the pressure has already dropped a bit to what it was before. So if we look at the simulation results, our actual demand went quite high. So we went to 33 meters per second. And our pressure, quite low. So you'll know this is below our 15 meters that we want to keep in the network. So to continue this, we can now, let's try 100. This is simulating a larger burst, less resistance for flow leaving the network. Now our pressure is near zero, and our actual demand only went up about another 5 or so liters per second. And so we ask ourselves, because now we're looking at a pressure-dependent flow, so the flow is dependent on the available pressure, and if we have higher flow rates coming to this particular node, we have higher head loss and thus lower available pressure. So when we increase this, we get a higher flow rate, sure, but we also, our available pressure now is quite low. So you would expect that if we increase this and we permit larger flows coming through the network, will we get a much higher value than 30, 38, 40 liters per second? Let's find out. Now we have zero pressure, and we basically have the same flow rate because there's no available pressure for us to pull our water out of the system. So there's the impacts, and you'll be able to. We want you to comment on these factors and include this in a small, very small, brief report, and you'll do that on another network. Do the same activities on a network from Bristol Water. So this is an operational network that you'll have all the demands and reservoir heads just as you do in the Pescara network. So you'll go through simulating the critical link analysis, introducing the local head loss, and a pipe burst as we just did now. Okay, thank you for listening, and I hope that was helpful in using EPANET to model hydraulics and water distribution networks. Thank you.